This question didn't actually give me the integral piece. It just said find the area bounded by the graph, the x-axis, and some vertical lines. Where if you were to graph 2x squared minus 3x plus 2, okay, you know you're dealing with a quadratic. If I'm going from 0 to 2, I could plug in a 0 here, and I know that I would have a value at 0, 2. I could also plug in a 2. I would end up with 8 here, minus 6, so that's 2, plus 2, that's 4. So I know I'm going to end up with a value at x equals 2. Sorry, here we go. 1, 2. I'm going to end up with a value of about 4. So my quadratic looks like it's going to kind of be like so. Close enough. That's not really important or essential to the work that we're doing, but just so I can get a visual of what's happening. I've got this quadratic, 2x cubed, make that a little smoother here, 2x squared minus 3x plus 2, and I'm bounded by the x-axis 0 and 2. So x equals 0 is right here, and x equals 2 is right here, and the x-axis is right there, so it's asking me for that area. It's asking me for the integral. It's asking me to use the fundamental theorem of calculus. It's saying I want to know the integral from what to what. Well, my boundaries were given to me. From 0 to 2 of 2x squared minus 3x plus 2. But it didn't actually ask me for the integral here, but it's up to you to recognize that you're going to use the fundamental theorem of calculus. So let's go ahead and work through this. I'm going to end up with, looks like 2/3 x cubed minus 3/2 x squared plus 2x. So all of that's going to be evaluated from 0 to 2. So I'd say big F of 2 minus big F of 0. Just got to do a little plugging in now. So 2 cubed minus 3/2 times 2 squared plus 2 times 2 minus, oh, how convenient. That's going to be 0, 0, and 0. Well, I'm not going to do a lot of extra work for that. I'm just going to go ahead and do a 0 right there. That's going to end up with 16/3. That's 8 times 2, by the way. So this is 8 times 2. That's 16/3. Minus, that's going to be 12 over 2, which is just 6, plus 4. So that's going to be, let's see here. This is negative 2. So 16/3 minus 2, 16/3 minus 6 over 3, minus 6 over 3, that's going to be 10/3. So that is the exact area between the curve and the x-axis from 0 to 2. That's one of the ways that you might see fundamental theorem of calculus used or assessed. Now last thing I just want to mention, and something that we've already briefly talked about, but remember, when we take the definite integral, when we evaluate an integral from a to b of f of x dx, that is what we consider to be the net area. It means that some of the area is positive and other areas negative. Anything below the x-axis is going to be considered negative, so we call that our net area. Alright, so if I had something like this, that gives me a little bit of that sinusoidal graph. Alright, go ahead and stop that. I'm going to call this B, I'm going to call this A. If that's region 1, and that's region 2, and that's region 3, regions 1 and 3 are positive because they are above the x-axis, and region 2 would be negative because it's below the x-axis. Okay, that's the idea of net area. Total area is something really important, actually, because you're going to get assessed on that quite a bit. But you have to recognize that it makes everything positive. So I am integrating from a to b, but I'm integrating the absolute value of f of x. So whatever was negative, I want it to be positive. That's what gives me total distance. So same graph. See if I can make it as accurate as possible. There we go. Close enough. Kind of looks like the other one. Okay, it's going to take this piece and it's going to reflect it to where now it's above the x-axis. So now that's region 2. So now it's reflected. So now everything's considered to be positive. Region 1's positive, region 2's positive, and region 3 is positive when we deal with total area. So I'll take that piece. It was like this, right? And it took that and reflected it. So absolute value. Now it's important, I'm going to just make a note here. It's important that it is not the absolute value of the integral from a to b of f of x. All that does is take whatever the integral was and make that number positive, and if the number happened to be negative. And that's not what we want. We want to actually make the function positive. Okay, so be really careful with that. Make sure you put the absolute value signs around the function, not around the integral itself if you're doing something in the calculator. Now the last thing I need to talk about, I don't have a ton of room, so on my notes online I just kind of squeezed it in, so I'm hoping y'all can do the same thing. All of this information is assuming that integral from a to b, that a is less than b, that the a is on the left side, that we're actually integrating left to right. So all this information that we're talking about is assuming that we're going from left to right, which is pretty typical. So that means that the area above 0 is going to be, the area is greater than 0 if above. I'm having a hard time squeezing this in. Let me rewrite that. So area is greater than 0 if above. So this would be regions 1 and 2, right? 1 and 3. And then the area is below 0 if below. I should say less than 0. Okay, so we're dealing with negative area if it's below the x-axis. We're dealing with positive areas if it's above the x-axis, if I'm going left to right. However, if for some reason my limits of integration are not in that order, then it's going to be changed. So it's vice versa. Okay, vice versa. Sorry, that's vice versa. If integrating right to left. Right to left. So again, I know there's not a ton of room here, all right, but I'm going to go ahead and squeeze this in. Hopefully you have a little bit more room over here than what I can fit in. So if we're doing area is going to be less than 0 if above, and this doesn't go, by the way, this information doesn't go to this graph, okay? All this information kind of goes together, and this is the only place that I could put it. So if the area is going to be greater than 0, or positive, if it's below. And the reason why that's true, the reason why that works, is because remember the integral from a to b is the same as the negative integral from b to a. So whatever was positive for this is going to be negative for this. So you do have to pay particular attention to your limits of integration. We can assume that about 90% of the time we are going left to right, but if for some reason we're going right to left, we have to consider that information. So don't forget that when we think about net area and total area. Same thing is just net accumulation and total accumulation. Remember, integration is an accumulation operation. So if we're talking about accumulating snow on the ground or accumulating a number of miles, okay, whatever it is, we're talking about total distance or net distance. That's going to be something that we have to consider as the limits of integration.